Okay, let's get started. So, any questions on last lecture's material? So, what's due tonight? Problem set 2 and quiz 3. Any questions on either one? Yeah. Number 4, yeah. Number 3. Part B, yeah. So, what's confusing about it? So it's an if and only if question, right? So how do you prove an if and only if statement? Yeah, prove it both ways. Okay? Hopefully that helps. The reason why it has like 2 or 3 points is like it's not meant to be a hard proof. Yeah.
In that same problem, can you explain what you mean by steps? In as much as
what's the context of the
accepts W and at most I?
I steps, I transitions, same thing. And sometimes I confuse the word steps and transitions, but I mean it to mean the same thing. Yeah. So hopefully this helps. If I have a machine that always moves right and I force it to work in at most I transitions, could I use more than I cells of the tape? No, or see more than I cells of the tape. So hopefully that helps. Note, we have these I copies of this sigma character, and I force the machine to operate in at most I steps. So I guarantee I won't use more than I need. Question?
What do you mean when you're talking about existence?
So something exists. So this will really help. What is the definition of a decidable language? No. What is the definition of a decidable language? There exists a Turing machine that always halts. Okay? So that should really help. So the key here is that the machine and the input that you have are fixed. So if I run that fixed machine on that fixed input several times, will the answer ever change if it halts? No, it won't change because it's a deterministic machine.
It's still run forever. But it doesn't have
Yeah, but the answer of whether it halts, for example, or accepts the input is exactly the same.
True, but don't we need to know whether it halts?
But the answer is always the same. So it's either going to be the language L equals the string containing 1 or the other one. Right?
I understand that.
So it's definitely one of those two. What is the definition of decidable language again? There exists a decider. Can you decide any finite language? Yeah. So that should really, I actually almost gave too much away there.
Follow-up question on that, just to clarify. So the M for L equals 1 is different.
Yeah. So L is completely. I don't even care what the language of M is. So L is going to be either this one string or this other string, depending on whatever M does on W.
But is that M the same for both of those languages, or is it different?
Yeah, it's the same. Yeah.
Fourth one.
Yeah.
Should we show that L reduces to ATM, or it is given that L reduces to ATM?
I didn't understand.
Should we show that L reduces to ATM?
Yeah. So it's.
So it is answered.
Yeah, I think that's what it says. It says L reduces to ATM, right?
So to prove that.
Yeah, to prove that, yeah. So for example, you can assume that a decider for ATM exists, then there's a decider for L. Yeah.
Back to problem 3.
Mhm.
So if we can only look at I cells on the tape, and we've already consumed some K cells traversing through W.
What do you mean looking through W?
So W is on the tape.
Yes.
So we've already made some number of state transitions before we've even gotten to pound.
No, I'm not simulating like some arbitrary machine. I'm saying that there is a machine that decides this. I'm not simulating M. I'm simulating the. I have a machine that is simulating individual transitions of this machine, but the machine doesn't operate on the W part necessarily. For example, it could, let's say W is here on the tape and then sigma I times here. So like the machine B could, for example, look in its transition function, look at some character of W and then traverse over here and then start working over there. So you can think of this area as like recording computation. So like if I happen to run M on W, then a simulation of it could be happening over there. That's essentially what B is supposed to do. Other questions?
In regards to the LBA part of this,
Mm-hmm.
I was kind of confused, like how we tied in with an LBA.
Well-
I feel like
Well, how many sigma characters are here? Or in the definition, I have I, but something. And I require that M halts on W within I steps.
Yeah.
So will I use any more symbols than over here if I'm simulating over here?
What do you mean by simulate?
So if I simulate M on W, ignore the W part at the beginning and the pound sign. If I just simulate M on W, will I use more tape than what's right there? More than this part right here?
No.
No, because even if I always move right, I will. I won't hit the very end. I won't need to have any more tape cells. So in fact, if M accepts W, then there's some value of I for which I don't need any more than I cells.
But this is within the LBA's
Yeah.
input on the input tape.
Yeah. So like for some value of I, like if I keep increasing I, the LBA's tape grows longer to accompany the input size.
Yeah. But then when we,
So if M does accept W, then there's some value of I that works.
and that M accepting W though, it isn't really happening on the input tape though. It's behind the input tape because M is
What do you mean behind the input
like
tape?
it's not. We're not. M is not even in there, so we're not messing around.
No, M is a fixed machine outside of here.
Yeah.
yeah.
So when the LBA is running that, it must have M somewhere else.
Yeah. So it can like do something with its states, for example, like to accompany transitions of M. Yeah. So M is fixed here. Yeah. If I made this instead M comma W out in front, this would definitely not necessarily be decided by an LBA. But since M is fixed, then all I need, since it's a fixed machine, I can put it into the states of it.
Can we still fix M and then just have M within the LBA?
Yeah, so we're building it into the LBA somehow to accompany the transitions. So it's like, it sees this and it looks at the W here and it says, oh, okay, so now I look in the transition function of M by going to this state.
Okay.
So the details aren't really that important here. So it's just the LBA is simulating the transitions of M. Other questions? Any questions on the, yeah.
For the runtime programmer question,
Yeah.
so you assume that your program, you're running your program as
Not infinite, but arbitrarily large. So that just means you can always add more memory if you wanted to, like a Turing machine. So yeah, so we're not necessarily confined to the physical limits of our universe or multiverse. Any other question? Yeah.
So the reduced ATM
Mhm.
like we put some machine learning on decidable. I have one imply that everything is on decidable.
No, this would not necessarily imply anything. Because if I proved L was undecidable, then that would show ATM is undecidable. But we already know ATM is undecidable, so this wouldn't really tell us anything. So the reductions that we've been doing are the other way around, right? Like, but since we know ATM is undecidable, then we can now show L is undecidable. But this is not the contrapositive of the first, right? It's just only the converse, and the converse is not necessarily the same truth statement. So that's why L is a particular language. This does not halt on input or something. So for example, let's look at this statement. This might help a little bit. What's the contrapositive of this statement? Well, I gotta negate both sides and flip the order, right? So this is equivalent to saying L bar reduces to not ATM, right? It's equivalent, an equivalent statement. So hopefully that might help you a little bit, because since we have this funky ordering up here, if we turn it around, then that's an ordering that looks a little nicer. Another one that you might want to, actually no, that'll be sufficient. Yeah.
I'm just struggling because there's a few reductions or percent here, and I'm struggling to figure out if I've written enough, made it formal enough. It kind of just feels like how
since it's a high-level type thing, it's not really that important to be that precise. But as long as you can justify why your reduction is correct, like for example, you can just say run M on this input. It doesn't need to be like, or just, for example, like for I between 0 and 100 versus for 1 less than or equal to I less than or equal to 100, or it can be written in pure English. So it doesn't need to be completely formal. Yeah. The high-level ideas are much more important than all the details. Unless you're talking about like something really simple like DFAs, then you might need more detail. But like something high-level like this, you don't need all the details for that. Question, yeah.
With 4 again, we're trying to show that something's reducing into the other thing. Instead of creating deciders and stuff, can't we just show that the thing that we're trying to reduce into is a harder problem?
Well, how do you show that?
Can't we just show that all instances of, like in this example, L are contained within A?
That doesn't necessarily work, because that would show that that would imply that supersets or subsets, if you like, of a particular language that's undecidable are also undecidable. But we know that that's not true in the general case. It might be true here, but you wouldn't be able to prove it here, because the halt TM one, if you think about the one back in recitation about like not the one that halts, halt TM includes everything in ATM, because halt TM includes the times when the machine explicitly rejects the input versus ATM, which only accepts. But it contains infinitely many more instances. If it was finitely more, then you can claim that right away, but it's infinitely more.
But the other way around, if we were looking at ATM and going into the halting one, then we could say that all instances of that is contained within that one.
But that would still imply that a superset is still undecidable. That's why we did the reduction for it. That preserved the answer. That's the important thing here. So I'm expecting an actual reduction here. Other questions? So have you started pset 3 yet? So when does pset 3 due? Friday. Good, so that you know. So I was going to go over the test right at the beginning, but of course nature calls, right? So actually that's not the right phrase. But I have the quote-unquote test here. So I'm going to go over it at the end, because some people might come late because they might be delayed and whatnot. But I can, unless you have burning questions you need right now about the test. Unless you want to wait until the end. Any other burning questions before we? Oh, well, I should say, after the test on Wednesday, there will be a lecture. Just a small topic, but need to get forward on some of these things. No questions? Oh, yeah, go ahead. 75. Yes. Unless you want me to talk about the format now. Okay. So I'm not going to show this on video for obvious reasons, but so I'm going to switch to the dot cam. for this. Let's zoom out. No pictures, please. It's not the actual test, so taking pictures will give you nothing. Okay, so this is what you'll see. So Cody Coderson is a person who's been taking this class for like 10 years now. So yeah, so your first and last name will be pre. Oh, you can't. Sorry. I need to switch it in 2 places apparently. So this is what you'll see on the front test. So they will be alphabetically ordered by your surname. So why do I not say last name, but I say surname instead? Because believe it or not, some people have more than one last name. And so if you're one of those people, make sure you know what ASU knows your last name by. Okay? So because they're going to be alphabetically ordered by surname, official ASU surname, starting with A's in there and then just cycling through until the Z's. So this exam number thing is just for me so that I can sort the tests by alphabetical order when I start grading them. So 75 minutes, 150 points, and they're broken down this way. And then whatever, if you're taking option B, I'll scale it up to 200 uniformly. So nothing, you're not allowed to have anything except for cheat sheets, and you can have as many as you want. I don't care what you write on them. I don't care. I prefer that they're handwritten because you learn a lot better when you handwrite stuff versus when you type it, but do whatever you want. I don't care. I'm not going to collect them or whatever. As long as you don't disturb your neighbor, because the worst thing when you're writing a test like this is to be disturbed, obviously. And then, yeah, show will work. Any questions on this first page? Yeah.
You say no notes, but unlimited cheat sheets.
Yeah. I want to cover all the bases. So notes probably, yeah, I'll change that. Thank you. Any other questions about the front page? Oh, and I should say, the test will not be stapled, and please do not staple it, okay? Because some people in the past have tried to staple this. You may think that you're actually helping, but it's a lot easier for me because I want to be able to separate this into question 1, giant pile here, question 2, giant pile here, 3, 4, 5, instead of like one person, 2, 3, 4 people. So it just makes it easier for me, so don't staple it. Okay, so ready to see the test? Haha. Okay, no, it's not actually there. So this is the first question. It's just a bunch of, I'm going to have a whole bunch of statements here, one statement each, and over here too. So there are going to be 10 of these. Just say true or false as to whether the statement's true or false. If the statement's true, then give a very brief explanation for why it's true, and if it's false, give a counterexample. So this should be very clear on how to do it. So note the space in here. So this is a problem with people who take tests in this class. They write way too much, and they write a lot of things that are completely unrelated to the question. Or they think in the hopes that they get something right and then score some partial points. So if you write a whole bunch of nothing, what do you think you're going to score on that question? Nothing, right? And in fact, if you write a completely perfect answer and then keep writing and write something that's wrong, what do you think I'm going to do? I'm going to mark points off. So write only what is necessary. That's why I have in capital briefly write an explanation. Each of these, I already wrote the solution for this, for the test. They average, and I made it very verbose, 2 sentences each. So they should be really short answers. So more detail is not going to help you here. So just address what the question is, and life will be a lot easier for you. And then you can move on to the other questions as well. Any question about this first question? Yeah.
So if it's true, we give an explanation. If it's false,
Yeah, yeah. I should say, if it's always true, say true. But if it's not always true, meaning that there is a counterexample, then give a counterexample. Okay. So this is not one of them, but one could be regular languages are closed under union. Is that true or false?
Yes.
That's true. Well, why was and an explanation of why it's true is a closure property, and we showed that via the product construction. Okay, so that would be a perfect answer for that question. Or another one might be, what would be a good one? The Church-Turing Thesis shows that algorithms are equivalent to Turing machines. So is that true or false? I should say Turing machine deciders. Yeah, that's true. And why did we show that was true? So that we were able to increment a number in binary, right? And then we showed that we can now add two numbers together via repeated addition, and then multiplication, and then exponentiation, and then any finite time operation after that can be simulated by just a whole bunch of increments. So that would be an explanation of why that question is true. So what would be one that's false? Let's see. ETM is decidable. False. And how did we show it was false? We showed the reduction from what to what? ATM to ETM. And that'd be a perfect answer. Great question. So unless the question specifically addresses show the reduction, ATM reduces to ETM, which it obviously won't here, then just say we proved that in class. So like we showed the reduction ATM to reduced to ETM. But if the question says show the reduction ATM to ETM, you better not say we showed that in class. Believe it or not, people have done that. So I need to. So that's why I have the need to say that. Any other questions about this? So like 1 or 2 sentences each for each of these. Don't write paragraphs. And inevitably, people will write paragraphs. So don't write paragraphs here. Or really for most of these. Most of these should be short answer, or like actually short answers. But any questions on this one? Okay. So this one, so all the other questions are longer answers. So each of these will have some statements in it, and then what it'll ask you to show is prove or disprove this statement. So like if the statement's true, show that it's true, and if it's not true, disprove it by giving a counterexample or something like that. Okay? Any questions on that one? Oh, and another thing. You see that your ASU ID, so this is not a real person, so don't worry about that. So ASU ID and name will be pre-printed here, so you don't need to feel to write your name or anything. And so that like if I happen to misplace your paper in somewhere else, then I can always find it because your name's pre-printed on it. Any questions on that one? So here's question 3. So something to do with reductions, and then something to do with basmati. Okay? Any questions on that? Okay, so that should be pretty straightforward. Next question, question 4. First one is something to do with languages, in general with languages. This is something to do with a DFA, and this has something to do with regular languages. Okay? And then finally, the last question, something to do with a Turing machine variant. Okay? So because you're submitting problem set 2, you should be familiar with showing equivalence of the standard model with a variant. And there's extra points there. Based on that, but the entire question's based on this Turing machine variant. Any questions on question 5? Yeah.
So does it pretty much go up through like last lecture?
Yeah, so there's an announcement on this, but it includes everything through the course up through product construction. Yeah, and nothing else after that. So nothing today will be on there. Any other questions about this? Oh, and on the back of the last sheet, there's a page where you can do rough work if you feel the need to. Each of these spaces is much more than enough room to complete the answers. But if you feel like you need to do some scratch work or something, there's a back for that. But note that this is not graded. Okay? Yeah.
Just a general question. I noticed you put on an example that if you use pencil, it can't be regraded.
Right.
So
Yeah.
you use pencil first and then use pen later.
Yeah. So if you like write your answer in pencil and then trace over it with pen, that's okay. Yeah. You can definitely use pencil if you like, but it's just you forfeit the chance of being regraded. It's not like I'll take points off or something. So for obvious reasons. Any questions about the test itself? Yeah. Hey, he was first.
Is the format similar to like homework, or?
I mean, I just showed you the format.
Well, yeah, but I mean, the questions similar in style.
Yeah.
Okay.
Mm-hmm.
Can I ask you about what also is?
Google it.
No, like I solved the problem, but like, I still don't know.
What did you use to solve it?
What did you use to solve it, and don't tell the answer.
No,
What particular theorem did you use to solve? Hopefully that did give the answer away. Any other questions though about the test? So what day is the test? Wednesday. At the beginning or the end of class? Beginning of class, unless there happens to be a thunderstorm like this. So hopefully there isn't. But any last minute questions about the test? Okay. So let's turn this off. Go back to here. Any last minute burning questions before we jump back into DFA land? Oh, shoot, I gotta fix this. Any last? Okay, so what were we talking about right before, right at the end of the last class? So we covered what construction for DFAs? Well, yeah, this product construction that can work for the union of two regular languages, or the intersection, or the symmetric difference, or majority, or whatever, right? So, so the high-level thing that we were talking about is something called the regular operations. And I can't believe no one caught me on this, but I didn't define the regular operations. So these things are the three operations: union, concatenation, and star. So hopefully you know what those three are because we did them for decidable and recognizable. Are the decidable languages, so this is not on the test, but it'd be a good question anyway. Are the decidable languages closed under the regular operations? Yeah, because they're closed under union, concatenation, and star. And same for recognizable as well. Have we shown that they are closed for regular yet? No, which one have we done so far? Yeah, we did union and intersection, but that's in the same type of problem. So let's try to move on to concatenation. I love the multiple colors here. Okay, so what is the concatenation problem again? So if I wanted to try to show that, so let's say L1 and L2 regular, this implies L1, L2 concatenated together is also regular. And we showed that this is true for decidable, of course. But remember back when we showed that L1 and L2 decidable implies their concatenation is decidable. How did we actually prove that? Well, we made a decider that does what? Yeah, it looks at the splits, like empty string with the whole string, then one character with the rest, two characters in the rest, etc. And we tested the first machine on the first piece and the second machine on the second piece. If there was any such split such that both machines said yes, what did we do? Well, we accepted, because now we found a split that says, okay, this first part was in the first language and the second part was in the second language, right? Because that's what the definition of concatenation is, remember? So it's WX such that W is in L1 and X is in L2. So it's some string in the first language concatenated with some string in the second language. Will that same strategy work here for regular languages, for DFAs? Could DFAs, so could we try a split, like say empty string with the rest, and then try another split? No, well, why not? Why can't we do that for DFAs? Let's see, how many times could a DFA run through an input? Once. So I can't try another split. And even if we could, which we can't, think about this. So let's say that this is the string we have. And suppose that, yeah, there's the split that will help me here. Is that split given to me? No. So it's not like the DFA can just read characters and then see a split character and then transition over to the other machine, right? So the split's not really given to me. So in fact, this seems quite a hard problem for DFAs, right? Because I can't just retry the input like we could with Turing machines, right? Because I can always just store more on the tape if I needed to. So DFAs, it seems quite hard. So maybe what we can do is let's make the model a little bit more powerful to make this problem a lot easier, okay? So, and if we can do that, then we can say, okay, maybe this more powerful model can do concatenation and maybe star a lot easier. But the really interesting thing is that this seemingly more powerful model than DFAs is actually equivalent to DFAs. So in fact, and moreover, this more powerful model, whatever machine we have there, can be converted to a DFA. And there is an algorithm to do that, which is what we're going to do today. Cool. So let's see. What we would like is, well, I don't know where that split is, right? The split may be here, it may be in that middle place, or it might be at the end, right? I have no idea where the split is. So what do you think we can do about that? Actually, there might not even be a split, right? So what do you think we can do? So the technique that we're going to use, we've already seen before. So what technique do you think I'm going to say? Non-determinism. So the idea of, remember, non-determinism is if we have a lot of choices we can make, we'll pick one that will lead us to acceptance if there is one. If there is a choice that will lead us eventually to some final state, then we will make that choice. And if there's no choice, we'll just make an arbitrary choice. So maybe we can define a non-deterministic version of a DFA like we did for Turing machines. And we showed that Turing machines are equivalent to non-deterministic ones. And how did we show that? That standard Turing machines are equivalent to the non-deterministic variant. Oh, sorry? Yeah, we can simulate it. And what was the idea behind that? This computation tree, right? So if I have the starting configuration of the machine, it may have several choices it can make, and we went through this tree in what order? Breadth first search, right? Because I want to be able to traverse the levels of the tree. Okay, so we showed that they were equivalent there. Maybe we can hope to do so here. But of course, we have to define it first. So, a non-deterministic, can't spell, non-deterministic, finite automaton, so NFA here. And it's, like you might expect, a 5-tuple. And the parts are defined almost exactly the same. Where everything but the transition function is going to be defined exactly the same. So Q, sigma, the start state, final states are the same as in a DFA, but now we gotta define the transition function a little bit differently because now we want to be able to handle a non-deterministic variant. Okay, well, let's see. Well, the transition function, what was the transition function for a DFA? So what two things do I need to know where to go next? I need to know the state and the input symbol, right? And what will the transition function give me? The next state. So I'm going to leave a little bit of room. Right, so that was the one for a DFA. Well, if we want to handle, well, let's go back to the concatenation part. Well, let's suppose that I was reading this character, and now this NFA thing is going to guess, I'm going to transition over to the second machine, right? And then start reading the next character. Well, if we think about it for a second, if we have a state, and so this is in the first machine, and this is in the second machine, and of course this second state is the start state of the second machine, because we need to simulate the second machine from the start state. Well, what thing needs to appear on this transition? Can a symbol appear there? I'll get to that. So could WI plus 1 appear there? No, well, it shouldn't, because the second machine needs to start off from this split point, right? And so its first transition, or something like it, will better be WI plus 1. But if I go through the first machine and transition over, then I just read another character, which is not the original input, right? Which is not what I intend. So a suggested idea is to put an epsilon there. So this thing, I'll leave some room. So that thing is an epsilon transition. So what you're supposed to interpret that as is, I can traverse this arrow and not read any characters off the input. So for example, if I am in the first machine and I go to that state reading WI, then I have the now choice to switch over to the second machine's start state, having not read any characters, and then continue from there. And of course, there may be other epsilon transitions going other places, right? So it's not only in certain places. but I'm now allowed to have epsilon transitions because I want to solve this concatenation problem. Okay, well, let's see. What things can appear on a transition now? Well, definitely everything in the input alphabet needs to be able to appear, but what else should appear? The epsilon now, because I now want this epsilon transition to solve this problem. So what I'm going to change here is, instead of picking only from sigma for characters, I'm going to allow the epsilon, not a character here, but I'm going to allow epsilon transitions here. Okay, does that make sense? Or is everyone lost?
I'm kind of confused because I thought every language should have epsilon.
So this is separate than the string epsilon. Well,
Is that defined? What if we expanded sigma out? It would be a set, and then one of them would be epsilon?
well, so this is the set containing epsilon. So I'm sticking epsilon into the things that could appear here. I'm not putting it into sigma or anything, or the language or whatever. I'm just I'm making a set which has the things that I normally could put on the transitions, but now I'm putting this epsilon which could also appear on the transitions. We'll have an example. The transition diagram makes this a lot more sense. But let's see. Well, think about this. So maybe in the first machine, once I read this WI character, where should I be in the first machine? Should I be in a final state of the first machine? Yeah, I better be, because that indicates some string that the first machine said yes to. So let's think about that for a second. So maybe we have a final state here of the first machine. So let's say first machine. And then we have another final state. And then the second machine's over here. And the start state of that machine is there, and it does whatever. Well, of course, now I need to be able to handle, I want to have these epsilon transitions go across the gap here, right? But what I might also want is, well, remember back to non-deterministic Turing machines. Could I have, so before I could have one possible transition to apply. But of course, now I can delete transitions and have 0 things to apply. Did we have more than one transition we could apply for a non-deterministic Turing machine? Yeah, so let's actually do the same thing here. So an example could be this start state of this second machine has 2 transitions that are, 2 different transitions that are labeled the same thing. So could a DFA have that sort of capability? No, because it's deterministic. It must have exactly one arrow of each symbol. Okay, well, let's see. Well, once I pick this state that I started from, and whatever symbol that I want to work with, how many states could I go to? Could I go to all other states if I wanted to? If I had a transition that's defined for that? Yeah, sure. Could I have one that goes to 0 other states? Like maybe there's a missing transition here for symbol B. Could I have that? Yeah, we had that for non-deterministic machines. Wait, so it can go to any subset of the set of states. Well, I can't go to just one state anymore. I need to go to any possible subset of the set of states. So how do we denote that? Any subset of Q, power set. So just like with non-deterministic Turing machines, we can go to any subset of the set of states. So I think this is ripe time for an example. So let's consider this NFA. So it'll start looking at like a DFA, but then it'll start to change a little bit. So this one's in the notes as well. So example. So let's see. Does this NFA accept the input 110? Yeah. So how do you actually determine that? Well, follow in what way? Well, I have two transitions labeled 1 now. So which one should I pick? The one that goes in Q0. If I happen to pick the one that goes to Q1, what would happen? I couldn't continue from there, right? So remember, DFA will only accept an input once it's read its entire input. But if I tried 110 here, and I went to the 1 for Q1, then I'm stuck. I can't read any more of the input, so there's no possible way I could accept the input. Okay, well, let's say that you weren't able to have that insight, right? You wanted to be able to work through this in a mechanical way. So let's see. What could you do? So I have to start in Q0 no matter what. Right? And let's try to simulate this string 110. Well, what possible things could I do on that input 1? Well, I could either take the self-loop transition on Q0, or what else could I do? I can go to Q1. So in fact, let's do a computation tree style simulation again. I actually just realized that that has a nice connection, but I didn't know that. So I could either stay in Q0, or I can go to Q1, right? So I can do either of those things. So if I happen to make the choice Q0 goes to Q0, well, now what are the choices I can do? Well, we consume that first character. Now what character? Well, we're back at 1 again. So I think we're in the same situation that we were before. So Q0 can do both of these possibilities again. But go back. Can Q1 do anything now? No, because there's no transition on 1 coming out of there. So in fact, this computation just died on that path. Okay, and let's see. So we knocked out that second character. What character are we looking at now? At the 0. So what can Q0 do on 0? Yeah, the only thing it could do is stay in Q0. So let's simulate that. So that's nice. What about Q1? What could it do on 0? Yeah, it can go to Q2. So we knocked out that third character. Do we have any more input left? No. Did we accept this input? Yeah, why? Yeah, so one of the paths said accept. Do I need all paths to accept, or at least one? At least one. Because non-determinism works by making the right choice. Right? So an NFA does not do this brute force simulation idea. So some people who teach this class, unfortunately, think that non-determinism is parallelism unlimited, right? So it's not doing this brute force simulation, but it's making a choice every single time. It makes one choice every time. So in this case, the NFA would make these choices because we got lucky and we saw that there was only one way to go to a final state. But it could have made the other choices, but it won't, because since there is a way to accept, it will pick the one that works, or a one that works.
You said that several times. I don't quite understand. How does it know? How does it look ahead and know the way?
Right. So an NFA cannot possibly be built.
Oh, okay.
So we're deep into fantasy land right now. So this happens in theoretical computer science, actually academia all the time. So we sometimes have this problem like concatenation, where the model that we actually do use is really hard to work with, but then we augment this model in some way to make it maybe not possible to build in everyday life. But what we do with that is maybe we can make this more powerful model, convert it into one that we actually can build. And we will do that here, which is nice. So just entertain this model for a little bit. We'll show that we can convert an NFA to a DFA. And so that's all I need. Yeah.
What if there are two paths that lead to success?
Right. So like, for example, if there happened to be something like this, so it'll pick any one that works. If there is a way, it'll pick a transition to apply.
That's like
Right.
non-determinism.
Yeah. So there was only one choice that works here, so we got kind of lucky. But it could have very well, if there was something like this, it very well could have chosen this instead. But if there is a way to accept, it will always pick one way to accept. Okay? Any questions about that? Yeah.
You said this is not an example of unlimited parallelism.
Correct.
Could you further expound on that?
Yeah, so an NFA, we'll define the computation formally in a second, but informally, an NFA will always make one choice. So it's not like doing a brute force simulation. Like a DFA only applies one transition because there's only one to apply. An NFA will, if it has many choices, it'll pick one choice. So you can think of it like there's a crystal ball right next to you, and it tells you, okay, apply the third transition, and then apply the fifth transition or something like that. So
It's magic.
yeah, it's magic.
Past.
Yes.
Okay.
This class has turned into magic now. So yeah, but it's just the nature of the model and the definition of non-determinist in here. But so it's kind of annoying, but we will get back to determinism by converting an NFA back to a DFA. Other questions? Okay, well, we don't have an epsilon transition in here, so let's actually have an example with epsilon transitions, and I don't have one, so I'm going to make one up. This is truly the hardest part of the class, making an example that shows something useful. Let's see. Okay, I think that's sufficiently complicated. So let's say that we want to test, let's see, ABA. So I had to brute force simulate it in my head, but okay. So we have to definitely start in Q0. But suppose for the moment, only for the moment, that there was, so I'll put it in a different color so you know it's not what I intend. Suppose that there was an epsilon transition from the start state to, let's say, Q2. So do I have to start in Q0? Yes, I always have to start in Q0. But before I've read anything off the input, where else could I go? I can go to Q2. Where else can I go? Q3, right? So if we have an NFA like this, we need to, if we're going to simulate it in some way, we need to look at everywhere we can go on epsilon transitions only. But I can't get anywhere else via epsilon transitions. But I didn't have that, so let's remove it. Okay, so the good thing is there's no epsilon transitions coming out of Q0, so that's good. So where can I go on reading A from Q0? Q1? Anywhere else? Can I go from Q0 to Q2 reading an A? After I've read the A. I only asked, when I read the A, where can I go? Only to Q1. Now, where else can I go without reading anything else? I can go to Q2 and Q3. So I'm going to put Q2 and Q3 down here. So we are simulating it in parallel, but the machine is not, if it's trying to simulate ABA. So we're just looking at all possible paths that could happen. Okay, so, and now we determined we can't go anywhere else, which is good. So where could Q1 go, so we knocked out A, where could Q1 go on B? It could just stay there. Can it go anywhere else on B? On B. Nope, can't go anywhere else. Fine. Can Q2 go anywhere on B? It can go to Q0. That's good. Can it go anywhere else on B? No, it can't go anywhere else. Fine. Q3, can it go anywhere on B? No, it has no transitions out of it, so that's good. Now, from these two states, where else can I go? Without reading any input. Well, Q0 has no epsilon transitions coming out of it, so we're fine there. Q1 does, and so now we add Q2 and Q3 like before. Okay?
So,
yeah.
Is that considered all one transition step?
Not quite, but because we're doing a simulation of it. If the NFA was simulating it, one way it could do this is the transition A, then the transition, the epsilon transition, then the B, then the A transition, then epsilon, then epsilon. But we're doing a brute force simulation ourselves. So we're trying to do this deterministically, which is actually one of the ways we can show we can convert an NFA to a DFA by doing this type of idea. Okay, so let's finish this up and then we can take a break. I promise. Okay, from these four states, where can I go on A? Can Q1 go anywhere on A? Nope, so we'll kill that one. Q0, where can I go on A? Q1, so let's put that there. And I can't go anywhere else on A. And it's pretty clear Q2 and Q3 also can't go anywhere on A. Great. Now where else can I go? From Q1, I can reach other places, right, via epsilon transitions. And we've already determined this, Q2 and Q3. And now since we did that, we have no more input. Do I accept now? Yeah, why? How can you tell? Because one of these final states, namely, one of the last states, namely that one, is a final state. Because now we finished reading the input. Could I, after seeing that last A, take more epsilon transitions? Yeah, I can certainly do that because I have no, even though I have no input, I'm not reading anything. So therefore, I can continue if I need to. Because we actually read this last A right here, we still applied the two other epsilon transitions. Okay, does that make sense? Or is everyone completely lost? I think, go ahead.
When you chose this NFA, it just made me think, why use epsilon transitions and not just have two A transitions from Q0 to different states?
Because if I, good question. So if I change this to like A and A, right?
Or I was saying Q0 has a transition to Q1 with A, and then another transition to Q2 with A, which is possible with an NFA, right?
Yes. So let's consider your example. Yeah. So that would not change the language, but so it's just another NFA for the same language. I just made an example out of the blue. So of course there can be many different looking NFAs for the exact same language. So I think it's a good time to have a break.